Okay, students, particle in a three-dimensional box of length L. So what is the Schrodinger equation? Time independent Schrodinger equation in three dimension, it is minus h cut square by 2m del square psi by del x square del square psi by del y square and del square psi by del z square, plus a v psi was there. And remember, again I take the particle to be free, that is no force acting on the particle, so we can safely put the potential energy equal to 0, and that is equal to E psi. Remember, in one dimension you had this, in three dimension you have this. So I won't solve this, or I won't show all the steps, but I'll show you the general solution. I think it is analogous to particle in a one-dimensional box. So again, psi is a function of x, y and z. So again, by the separation of variables technique, I can take psi, which is a function of x, y, z, to be a product of three functions: alpha, which is a function of x, beta, which is a function of y, and gamma, which is a function of z. And if we individually solve, you see, you will get alpha x same as psi x in our particle in a one-dimensional box. This is what you see, root 2 by L. This, remember, this was the solution for psi x for particle in a one-dimensional box. Sine, in this case, I'll put n suffix x pi x by L, where again kx, I'll put a suffix of x over here because it is three dimensions. So kx is nx pi by L. Remember, in a particle in a one-dimensional box, it was k equal to n pi by L, where nx is 1, 2, 3. In the previous case, it was n equal to 1, 2, 3. So just n replaced by nx, kx replacing k. Similarly, beta, which is a function of y, again will show the same thing, root 2 by L sine ny suffix y pi y by L. You can see again where ky is ny pi by L. Again, ny is an integer which can take value 0, 1, 2, 3, not 0. Again, gamma z, which is this, is root 2 by L sine nz pi z by L. Remember, in all these cases, we found the solution for this in particle in a one-dimensional box for psi x equal to root 2 by L sine n pi x by L. We have replaced n by nx, ny and nz, and instead of x in the y direction it would be y, and in the z direction it would be z, whereas nx, ny and nz are integers which can take values from 1, 2, 3 and all. Everything remains the same. So if this is alpha, this is beta, this is gamma, then psi would be the product of the three. So it will be 2 by L to the power 3 by 2 sine nx pi x by L sine ny pi y by L sine nz pi z by L. Remember, this z, this y and this x, they are suffix nx, ny, suffix nz. So this is the total wave function of the particle. Now remember, in one dimension it was, the energy was equal to pi square h cut square by 2ml square, n square. In this case, n square, it would be nx square plus ny square plus nz square because it is three dimensional. Now what about the ground state? That is the lowest energy state. The lowest energy state is when nx is 1, ny is 1, nz is 1. So nx, ny, nz is 1. So we have a 3 pi square h cut square by 2ml square. What about the first excited state? The first excited state is nx becomes 2, ny and nz remains as 1. Nx becomes 2, ny and nz remains as 1. So you have 2 square, 4 plus 1 plus 1, that is 6 pi square h cut square by 2ml square. Now you see, the same energy value can also be obtained if nx and nz remains as 1 and ny becomes 2. So 1, 2, 1 will give the same energy value. Another one, if nx and ny remains as 1, nz becomes 2, that is 1, 1, 2. So you can see, for all the three combinations of nx, ny and nz, you have the same energy values. But if you remember from statistical mechanics class about degeneracy, I told you what is a degenerate energy level. An energy level was degenerate if you have more than one state having the same energy. You remember? A single energy level having more than one state. I denoted states as boxes. So if you have more than one state all having the same energy, then that energy level was called degenerate. Now look at these 2, 1, 1. These are the nx, ny and nz integers. Nx, ny and nz integers. Nx, ny and nz integers. All the three different combinations have the same energy, but different combinations of nx, ny and nz will give rise to a different psi. Let's say nx is 2, ny is 1, nz is 1. So this will be sine 2 pi x by L, sine pi y by L, sine pi z by L. And for this combination, it will be sine pi x by L, sine 2 pi y by L, and sine pi z by L. And for this combination, it will be sine pi x by L, sine pi y by L, and sine 2 pi z by L. You see all these three different combinations of nx, ny and nz, that is 2, 1, 1, 1, 2, 1 and 1, 1, 2, gives rise to different wave function psi. And if you remember, wave function denotes the state of a particle. So these three combinations, different combinations, gives rise to different psi, that is different state, but all of them have the same energy value, 6 pi square h cut square by 2 ml square. So these three states are degenerate states. So the first excited state, which has this energy, is threefold degenerate. That is, there are three different states, because this combination, different combination of nx, ny and nz is going to give rise to a different psi, which implies a different wave function, which implies a different state. So all these three different combinations will give rise to a different state, but all having the same energy. That is, the first excited state is threefold degenerate. That is, there are three states, different states, all having the same energy. This is a very, very possible or probable Mac-out question. They tell you, prove that the first excited state is threefold degenerate. This is how you're going to prove. You need not write all of this in that question. Just write, we know that the wave function for a particle in a three-dimensional box is given by this. We know that the energy of a particle in a three-dimensional box is this. So the ground state is this, the first excited state is this, which can have three different combinations. So the first excited state is threefold degenerate, because these three combinations will give rise to different size, different wave functions or different states. So this was particle in a three-dimensional box. Now we are going to do some problems for particle in a one-dimensional box. So let us say they ask you to find the expectation value of position and the expectation value of momentum along the x direction for a particle in a 1D infinite well. I told you when I was writing the postulate of quantum mechanics that we will be dealing with problems and then it will be clear on how to find out the expectation value of any observable quantity. You remember the postulate of quantum mechanics that any observable quantity, the expectation value or the average value is given by minus infinity to plus infinity psi star. I told you to sandwich that operator between psi star and psi and integrate within proper limits. In this case, this observable is, say, x. So I'll sandwich the x operator between psi star and psi, and my limit of integration will now be 0 to L, because the particle cannot exist outside this barrier. So you remember I told you that if you operate x operator on psi, you will get the value of x and psi. That's the x operator. So now it is the value and I can multiply it. Previously I just cannot multiply. I warned you, you are not multiplying x operator with psi, you are operating x operator on psi. So by operating x operator on psi, you'll get the value of x, the position value, and psi, and now we can multiply. So what we have is, since x operator on psi is x and psi, so expectation value of x is, now since this is a value, I can take it on the left hand side and this becomes psi star psi dx, where psi we know from a one dimensional box is root 2 by L sine n pi x by L. So average value of x is psi star psi. Since psi is this, psi star or the complex conjugate of psi will also be this, because this is a real quantity. So root 2 by L becomes 2 by L, x is there, root 2 by L sine square n pi x by L dx, which is 1 by L I can take out because it is a constant, and I have 2 sine square theta, which means 1 minus cos 2 theta. So x into 1 minus cos 2 n pi x by L dx. Now if I integrate 1 by L is out, x dx, you can see from here, x dx, and minus 0 to L x cos 2n pi x by L dx, x cos 2n pi x by L dx. So the first integration is x square by 2, you put the limits 0 to L, and in the second integration, integrated by parts, minus sign is out, it is x is the first function, cos 2n pi x by L is the second function. So if I integrate it, sine 2n pi x by L by 2n pi, limit 0 to L, minus derivate x, we'll get a 1, and cos integration is sine 2n pi x by L by 2n pi by L, and another integration. So this is simply integration by parts. So if I'll put the limits, it will be L square by 2, 1 by L is a common outside, you see from the very beginning, 1 by L, so it is L square by 2 minus, now if you put a 0, you have a sine 0 as 0, and if you put an L gets cancelled out, sine 2 n pi, another, it is a multiple of pi, integral multiple of pi, so it is 0, so this whole thing is 0, there is a minus out, and here there is a minus. Integration of sine means minus of cos, so this becomes a plus, here there is a minus, so it is a minus, so it is cos 2n pi x by L by another 2n pi by L comes down, so it becomes 4n square pi square by L square, and it is 0 to L. Now if you put a 0, then cos of 0 is 1, and if you put an L, then cos 2n pi, so it is a integral multiple of 2 pi, again it is a 1, so 1 minus 1 will be 0, so again this term will give me a 0, so you have expectation of x as L square by 2 into 1 by L, so that is L by 2, L gets cancelled, is L by 2. So what is the average value of position of a particle in a one dimensional box? It is L by 2. Now it should be common sense, we have done so much of calculus, that is integration and all, to arrive at this solution of L by 2. You can simply give the answer by looking at the probability distribution which I had drawn. You remember the probability distribution was this. So this was mod of psi 1 square, that was particle in a 1D box. You remember I had drawn this. So you can see that the probability of finding the particle is right at the middle. This is 0 and this is L. Again you can see that the probability of finding the particle at the boundaries is 0 for all the cases. Again for all the cases. But you see, in the ground state, the probability of finding the particle is maximum at L by 2. So you can see that what is the average value or what is the expectation value of position of a particle. So if a particle is inside this box, maximum number of times you will get the particle at what? L by 2. So this is what you can expect. Similarly, for if the particle is in the first excited state, that is psi 2, this was the probability distribution. You can see that the maximum probability to find the particle is at L by 4 and at 3L by 4, because this gives the probability. So if I distribute or roughly say that the probability of finding the particle at L by 4 is half, and the probability of finding 3L at 3L by 4 is also half, because the total probability must be 1. So what is the average value of position? So L by 4, the chances of finding the particle at L by 4 is half, and the chances of finding at 3L by 4 is also half. So what is the average value of the position? It is this. So it is L by 8 plus 3L by 8, which gives me 4L by 8, and that is again L by 2. So what is the average value of the position? The average value of position is again L by 2. See again, if the particle is in the second excited state, this was the probability density distribution for, you remember, psi 3 mod square. Again, a particle has maximum chance to be found at L by 4, has a maximum chance to be found at L by 2, has a maximum chance to be found at 3L by 4. So if I divide my probabilities equally, so the particle has 1/3 chance to be found at L by 4, 1/3 chance to be found at L by 2, 1/3 chance to be found at 3L by 4. So what is the average value of the position of the particle? So 1/3 chance at L by 4, 1/3 chance at L by 2, 1/3 chance at 3L by 4. So L by 12 plus L by 6 plus L by 4, take the LCM, you have L plus 2L plus 3L, and what you have is 6L by 12 again and L by 2. So every time, what is the average value of the position of the particle? If you measure the position of the particle inside a one-dimensional box, you would, on an average, you will get the particle at right at the middle of the box, that is L by 2. Now this was just from common sense, but if you really want to work out the mathematics, this is the mathematics. Expectation of x, which we worked out, must be equal to L by 2. This is the rigorous mathematical proof, and that was common sense. Similarly, if I ask you what is the expectation value of momentum, again, expectation value of any observable quantity is given by the operator of that observable, that is px operator, sandwiched between psi star and psi and integrated within proper limits, that is 0 to L. So again, psi star, you remember the px operator was minus I h cross del x. That's why we did the operators first. Into psi, not into, but this operator operating on psi dx. So what is psi star? Psi star is again root 2 by L sine n pi x by L. This operator minus I h cross d dx, and psi is root 2 by L sine n pi x by L dx. So you differentiate this first, that is, you operate this operator on this first and then you multiply. So this is not multiplication of this and this is operation of this on this. So I have, but the constants can be taken out. You can see root 2 by L minus I h cross can be taken out. So that is 2 by L minus I h cross can be taken out. 0 to L. Sine n pi x by L remains as it is. Sine n pi x by L remains as it is. If you differentiate d dx of sine n pi x, you will get an n pi by L out and cos n pi x by L dx. So if I take n pi by L is a constant, I can take it out, and if I take in 2 in, then I have 2 sine theta cos theta. So you can see n pi by L is out. Here you have an L, here you have an L, so you have an L square. So you have 2 sine n pi x by L cos n pi x by L. So this is 2 sine theta cos theta, and that is sine 2 theta. So this is minus, the constant is again out, 0 to L sine 2 n pi x by L dx. So that is sine 2 theta. If I integrate this, you have a minus cos minus, and this minus will become a plus ih cross n pi by L square. You have a cos 2n pi x by L by 2n pi by L, and the integration limit is 0 to L. If you put a 0, you have a cos 0 of 1, and if you put L gets cancelled, 2n pi, so that is integral multiple of 2 pi. Cos of integral multiple of 2 pi is again 1, so 1 minus 1 is 0, so again you have a 0. So expectation value of momentum of a particle within a one-dimensional box is 0. So this was rigorous mathematics to find out expectation value of momentum. I did this in order to show you how to find expectation of any observable quantity. This is mathematically how you need to do it. We'll do many more problems on expectations, but for the time being, these two are very, very important. Now, by common sense, again, we can say that yes, the expectation value of momentum of a particle, x momentum of a particle within a box is 0. Within a box, a particle has, you can see, equal chances of having a positive momentum. Remember, momentum is a vector quantity, so it has magnitude as well as direction. So a particle can have a momentum along the positive x-axis, and equally chance is there that the particle also has a momentum, same momentum, along negative x-axis. So if you average all the momentum values, then definitely the average of all the momentum values must give you 0, because the particle can have positive momentum values inside the box, and since it cannot go out of the box, the particle will rebound, and the particle can have a negative momentum value. Again, it will rebound, it can have a positive momentum value. So there is equal chance of finding the particle with a positive momentum value or a negative momentum value. So on an average, the momentum value of a particle, if you measure it, it will give you a 0. Thank you. We'll do problems in our next class.